All right. If you were not here for the first class, you're okay. If you were not here for the last class, which was technically the second class, you need to go on the Moodle and you need to watch the video. All of our video lectures stream on there. So if you're ever absent, you can always go back and find out what's going on. Okay? I don't need biology notes. I need astronomy notes. Lost markers. Does somebody need to borrow one? All right. So, we talked about a number of things last class. Again, we'll just sit there and say this. This is where we're going today. These are coordinates. These three are all the same. Okay? They're all interrelated. We're going to answer all of it. This is kind of much. I want to start with some prayer before I get going. And then we'll go to the basics. Let's go to the Lord. Heavenly Father, thank you for reminding me to put you first here and to go to you and ask for your help, Lord. I just pray that would be our pattern, not only in this class, but in our lives, Lord, to know that there is no wisdom, there is no knowledge that comes apart from you. The fear of the Lord is the beginning of knowledge. The fool despises wisdom and instruction. Father, as we study these things about stars and masses and timelines and all of this, Lord, if we don't fear you, if we don't know you, if it just doesn't bring us to awe of you, then we truly have been fools. Lord, I pray that you would help us in all these things, to discern and to know what's true, and to study these things with a desire just to see your plan in creation, your grandeur in creation, your power. And we have light because you give light. Lord, as we study today and we look even at matter and antimatter, I pray that our hearts would be deeply troubled with the knowledge that no matter should exist. There should be nothing. Not a proton, not a neutron, not an electron. That all of creation is impossible apart from your will and your hand. I pray that would just settle in our hearts, and wherever we have other thoughts, that they would be deeply disturbed by that truth that science demonstrates us. Father, help me to teach these things well and to be clear, good understanding. Each of our minds to have a sense of what we do and don't understand, to be humble enough to ask questions where we need to make sense of it, to study diligently. We pray these things for our good and for your glory in Jesus' name. So we're studying stars. At core, what is a star? Mass of gas. It's a big old ball of gas. And that big old ball of gas is very hot. But at one time, that big old ball of gas was bigger, at least in terms of volume. Not mass, but volume, right? Volume. Think about something like density. It's the idea of mass over volume. As I contract some, think of a loaf of bread. It's a great example. I can have a loaf of bread, and it can weigh 2 pounds. And it takes up this much volume. And I squish it. It takes up a much smaller volume, but it still weighs 2 pounds, right? The mass didn't change, the volume did. I made it a lot denser, okay? Same thing with the gas. It's out there in the cosmos, and I can have a big old mass of cold, really cold gas. But due to the force of gravity, it kind of begins to contract, and slowly it will heat up, right? And it will get more dense. It's going to have the same mass, right? But due to that force of gravitational energy, it's going to begin to heat up, right? Now, at some point, it's going to go from just being a big old ball of gas into being a star, right? And what is that point? Remember me talking about this word? When do we cross from just being really, really hot gas into actually being a star? Fusion. Fusion where, by the way? Right idea, wrong word. Core.
Yeah, sorry.
Yeah, no, you're good, man. It's you know what you're saying.
Translation to my language is the same.
Amen. So, it means the same thing. So when you're having fusion in your core, and any star that has fusion in its core, we've said, is on the main sequence. Every star at some point, if it's a true star, if it's doing fusion, it's going to be on the main sequence. If you don't know what that word is yet, that's okay. You'll catch it when you go back and watch the video, or you'll catch it as we get to it. Do me a favor, if you got headphones, just take them out. Just simple thing to help me and my weak, sinful heart. I feel like you're being whatever. So we're going to move on. So stars are doing fusion in their core. That's what makes it a star. It's going to be doing that in the core for 90% of its life. And then things will begin to change drastically. We talked about the structure of a star last time, right? All of its different layers. What were those layers? What's the first layer? The center. It is the core. What's next?
Radiated zone.
Okay. And what's happening in the radiative zone? I've got some arrows. What are those arrows doing? They're going out. They're simply going out. I'm not gonna, well, I am going to draw them all. Hopefully you already have this, right? So you're not too worried about this. This is the radiative zone. Let me do this in color because it'll be easier for you. Do you have to know this?
Yep.
In order. I'm going to give you just a star with all these layers, and you're going to have to draw or label them, okay? Remember, not that tough. You know what's coming. Just, you're either going to learn it or you're not, right? But no. All right. Radiative zone. What's the next zone? Convective. Hands up. Fingers out. Show me convection. That works, right? It's the idea. If you were doing it backwards, that's fine, because you're not back. I mean, it's just it's the idea that it rises, gives off its heat, and falls back down. It's simply, it's a density and temperature thing, right? Warm air rises. What happens once it rises? It gives off its energy, and then it cools and falls back down. This happens everywhere. We see this everywhere. This is simply physics. So that's what's happening here. It's getting energy all the way from the core. It's passing through the radiative zone. It's heating up material in the convective zone. It rises, gives off its energy, and falls back down, right? And so that is what is happening here. Now, if you don't have this drawing, I draw this. This is worth knowing. Okay. So this is the convective zone. What's the next zone or layer? Photosphere. What does the word photo mean? Light. What's so significant about the photosphere?
Yeah. It's red.
No,
we see.
that's chromo.
The first thing we see.
It's the first one you can see. You can't see inside of this. This is the light that you can see. It's being generated here. Okay. There's a certain density, a certain opacity, which means you can't see past it. That's happening here at the photosphere. The next layer, chromosphere. What does the Greek prefix sphere mean? It's like just me asking you what's a sphere, right? How would you describe a sphere?
Sphere.
It's
Give me the
circular,
yeah, like
circular ball.
circular in 3 dimensions. We call that it's like a ball, right? Okay, good. So you understand what a sphere is. What does photo mean?
Light.
Light. It's a big old ball of light. Chromo.
Color.
Color. It's a big old ball of color. What color does this happen to be? Red. When can you see it? During eclipse, right? It's a big old, well, it's actually pretty thin, bright red ring that surrounds the shadow of the moon. And then the outer layer? The corona, right? Which means? Crown. Which one of these is, well, I mean, I guess I kind of showed you by drawing it. Which one of these is like the largest layer?
The corona.
The corona, right? Where are we? on Earth.
Corona.
We're in the corona, right? I mean, the way it's defined, the corona actually extends out well past the Earth. Okay? This is where solar weather happens. This is where it's where solar wind and electromagnetic pulses and things come off of this. What drives everything here? That's not bad. I appreciate that. We've got to put it in perspective. Gravity and mass, those are two factors. Let me rephrase this. What's making this hot?
Fusion.
Fusion. Where's fusion happen?
The core.
Only in the core. Okay. Now I want to go back and look at this. We did a graph. Right. And let's see. You guys remember what this graph looks like? Yeah. Yeah. So I got my temperature here, right? And which way is temperature going? Up or down? It's going up. Okay. Good. And what's happening here? Distance. Distance from core. And which way? This way, right? So we're getting further away here. So if I just think about this logically, the layer that's furthest from the core is going to be which layer? The corona, followed by the chromosphere, followed by the photosphere. And we're not worried about these inner layers, right? I only asked you to know one temperature. 15 million. What's 15 million? The core is. Okay, so we just kind of have this baseline. Core equals 15 million degrees Kelvin or Celsius, or it doesn't matter. It's hot, right? Okay. All right, my first layer, what is it? On this graph, what is it and where's it go? Photosphere. It's kind of going down, right? And then what happens? And then it goes up. Okay, and then what?
Chromosphere.
Huh?
No, out. It flats out at the chromosphere.
Kind of flattens out. Let me see your guys'. Let me see yours. My chromosphere, is it hotter or cooler than my? It's not. And I flatten out and then? Again, how?
Straight up. Goes straight up.
Straight up. We do a little bit of this, right, and then. Is that right? That's about what you guys have?
Yeah.
Good. What's happening here? It's the photosphere. What is this? Chromosphere. This is our transition. What do we have here? Corona. Right? Notice that our corona gets, in places, hotter than the core. Incredibly far away, much less dense, and yet, and so we don't understand this. Why? But there are regions of the corona that are hotter than the core. Okay? In fact, a lot of this is counterintuitive. You would think, think about this. If you were in a house over the last couple days, it's freezing cold outside, and the only source of heat is a stove, where do you want to be? You'll be right by the, I'm talking like wood burning stove, right? I'm not just talking like your mom's cooking oatmeal or something. Like, I'm talking a big old wood burning stove, but it's freezing outside. You want to be right by that fire, right? And yet this is saying that as I get further away from the fire, I'm going to be hotter. That is completely counterintuitive, isn't it? It's why this, I want you to know this graph. It goes against everything you would think.
Heat does just dissipate with the fire too. It's just that we get so far away relatively that it does get cold again.
Right, and yet that's not what's happening with the sun. You know what I'm saying? You would expect here's my core, right? 15 million degrees, you'd expect, okay. So here's my core, and then, all right, well, it's going to be a little less hot in my radiative zone. Okay, it'll be a little less hot in my convective zone, and the photosphere, and okay, well now the chromosphere, and then there's almost no material, and we're very far away by the time we get to the corona, right? I mean, you'd expect something like that. But instead, we get this. That's kind of wild. And particularly when it comes to what's happening in the corona, I mean, this is a huge jump. All of a sudden, we're heating up like crazy. And we don't really know why.
The radioactive energies stuck in the corona area, and it's intensifying the heat or something?
I don't think so.
No?
I don't think so. All right. No, it's fine. So, but the key thing now, having reviewed that, the key thing moving forward is this. This thing being so hot, giving off the energy that's driving everything else. We want to know, what is it that's happening in the core? Where does the energy for all of it come from? And how does, the answer for these is nuclear fusion, right? So as we explore these, we're also going to answer, well, how does nuclear fusion work? Okay? So I guess a simple answer for the first part is, what's happening in the core? Fusion. Where does the energy come from? Fusion. Where does the light come from? Fusion. Where does the heat come from? Fusion. Fusion is the answer. What is fusion? An easy word to say. What does it mean to fuse two things?
Combine.
Combine. Okay. What are we combining?
Hydrogen.
Hydrogen. And what are we making?
Helium.
Helium. Anybody happen to know the atomic mass of hydrogen? One atomic mass unit. Do you know the atomic mass of helium?
Is it 2?
It's 4.
Yeah, 'cause there's 2 neutrons.
Standard. Okay. Helium is not exactly 4 times the mass of hydrogen, though. It's just a wee bit less. But it's just made up of hydrogen. All we're doing is slamming hydrogens together, and we're making helium. And yet helium's coming out a little less massive than the hydrogen that you started with. Now, that's not supposed to be possible. We have laws of physics, like the law of conservation of mass, that says whatever you put in is what you have to get out. We have laws of energy. It says conservation of the law of energy. Whatever energy I put in is the energy I put in has to be the energy that comes out. And yet, I have less mass than I put in, and I have more energy than I put in. So what happened to my mass?
Converted energy.
Converted into energy. I want you to think about that just a little bit, okay? I have less mass coming out than I put in, but I have more energy coming out than I put in. Somehow that mass and that energy have to equate to each other. You've heard of it. You've seen that, right? You've heard of it. And I'm not going to, when I say you've never understood it, that's not an insult. I don't understand it. It's so above my pay rate. I mean, I can tell you what it means. I can do the math. I can all that. How on earth he came up with that? And yet it's true. It's true absolutely everywhere. You can convert energy into mass, and you can convert mass into energy. And that's what's happening in the sun. And that's what we're going to look at, right? So I'm going to erase some of this stuff, and we're going to really get going on today's material. By the way, did you need to know that graph? Yeah. What do you have to be able to do with that graph?
Recreate.
You gotta be able to label it. I'll give you the graph. I'll give you the shape. I'll give you all that. You gotta be able to lay it. Tell me where the layers are. Tell me what's happening on those axes, okay? That's all you gotta be able to do, but you do have to be able to do it. Each little part that you label correctly will be a point, okay? All right. Make sure I got everything I want here. Not just take you willy-nilly into the weeds here. Two things I do just principally want you to understand. Law of conservation of mass. Have you heard of this at least, hopefully? Okay, all this is saying is matter can be neither created nor destroyed until Einstein's born, right? It says matter cannot be neither created nor destroyed. I want you to think about that. We're going to think about this for a minute. Go ahead and write that down and we're going to talk about it. I have 4 little children. Theo's 7, Luke and Kate are 5. Benjamin will be 2 on Valentine's Day. He's a handful. They're at just the right age to appreciate what I'm about to tell you. So I'm going to make up an experiment. Okay? Theo decides he wants to do a volcano. So he builds a volcano out of clay. And he's going to put some baking soda in there, and he's going to put some vinegar in there, but his father is a science teacher. So of course he's going to go get a little kitchen balance, and he's going to weigh out the mass of baking soda. And how much is the baking soda's mass? Give me a number. 3 grams. Okay. And what's the mass of the vinegar he's going to use? 5 grams. And, you know, he's a smart kid, so he knew I'm going to need to measure my volcano's mass also in advance. What's the mass of the volcano? Say 10. Good. That's a nice number I can work with. 10 grams of volcano. So he performs the experiment, he gets the fizz, everything's good. He takes the new mass of the volcano plus the baking soda plus the vinegar, and he's expecting it should weigh how much?
18.
Should weigh 18 grams, but it doesn't. It weighs 17 grams. He goes, Dad, mass disappeared. What happened? Well, son, you made a mistake in your experiment. What was his mistake in his experiment? Tell me.
He didn't account to it for the reaction causing creation of some gas.
Yeah, he didn't measure the mass of the gas. How fun is that to say? Anyway, that carbon dioxide that came off, that was matter. It had mass. You ever think about that? I don't have a scale. I'm doing. Dude, I have a scale. It doesn't have a thing. I can't do this. Oh, that stinks. I actually do have balloons. If I had a balloon and I took its mass and it came out to 2 grams and I blew it up, is it still going to be 2 grams? No, it's going to increase in mass because the air I blew into it has mass, right? So if my son does this experiment, I'm going to lose mass because I failed to account for it, right? But if we did this experiment in a vacuum, or if you did it in a balloon, and you could do that actually, then you would expect it to come out as 18 grams. That's a very reasonable assumption because matter can be neither created nor destroyed, right? Then there's also the law of conservation of energy. What do you think this is?
Energy.
Energy can be neither created nor destroyed. Now, I left a little something on both of these. In the example of the chemical reaction, it was sure, but it was converted. Hydrogen ions combined with hydronium ions, they produce water. Carbon atoms, oxygen atoms were reconfigured, produced carbon dioxide. Nothing was destroyed, but atoms were literally rearranged like little Lego pieces. When it comes to energy, it's a little different. So your batteries, your phone's dead. What do? You charge it. Plug it in. Gets up to 100%, and you use it throughout the day, and then it goes back to dead. That energy wasn't destroyed, right? That implies it got destroyed. What did it get? Speak scientifically to me. What happened to that energy? What happened to your 100% charged battery? It got transferred. The energy of the because that electricity is the flow of electrons. So you used electrons to charge up your batteries, just chock full of electrons, ready to go, ready to do work, and at the end of the day it was back down to, we ain't got no electrons left. Where do the electrons go? Because I know this, your phone's cool, but your phone is not a taser. You're not just walking up like, giving it people the business. Where did your electrons go?
All the components of the phone.
Give me more. Light. Some of it got you can see your phone. Some of it just got converted to light. Right? Good. What else?
Heat.
Sound. Think about that. You got your phone and you're using it for quite a while and you put it in your pocket and all of a sudden, like on a cold day, your phone's warm, right? That's energy. Those electrons got converted into light, which heated up your phone. It got converted into heat. You said sound. Sound is particles vibrating, moving. How did they start vibrating, moving? Your phone used energy to move speakers back and forth, right? And so it got turned into mechanical energy, and chemical energy, and light energy, and heat energy. And so it's transferring from one form to another. The law of conservation of energy says that's all fine. But whatever energy you put in better be the energy that you get out. But it can't be created and it can't be destroyed. It's got to be conserved. Except for in the sun. Because in the sun we get out more energy than we put in. In the sun we get less matter out than we put in. Right? And of course, again, all I'm doing is trying to just conceptually reinforce this whole idea of E equals mc squared. Okay? We know this is happening through fusion. But fusion itself requires a certain amount of energy. And I am out of sequence for our thing, but that's okay. How hot do you think you have to be to do fusion? To take hydrogen atoms and get them to collide into each other with such force that they stick. And why is that a problem? Because it is a problem. Y'all like magnets? Okay, your basic magnet's got two what? North and south pole. And if I stick north to south, what do they do? They stick. But north to north, what do they do? And it's a fun thing you can do. You can take two north poles of a magnet, and you can like sling them at each other, and those magnets will get real close, and then they go, right? They repel. What's the charge on a proton? Say positive.
Positive.
What's the charge on the other proton? Say positive.
Positive.
So I take two things with a positive charge and I shoot them at each other, what are they going to do? They want to repel. Okay? So there's got to be something else that's going to allow them to stick together. And there is. It's called the strong nuclear force. You're welcome. The strong nuclear force is strong enough to overcome the repulsion of like charges. That was a good question. You want to write this down. The strong nuclear force. I better write this down. I better not just repeat it. Where am I at? Can I erase this? Everybody good here? Okay. Holy moly, God. Have I explained to you why it's always so hot in this room? Or in the summer why it's so cold? We share a thermostat with the room on the other side, but the thermostat's in their room. And in that room right now, it's cold, I guarantee you. A new teacher, brand new room, he doesn't know that I'm stuck on the same one. It's probably 67 degrees in there right now, so he's like, I'm gonna at least get this up to 69. Meanwhile, it's 95 degrees in here. And I've got the vent shut. I don't know what the problem is, but it's rough. And in the summer, it was the exact opposite. I was always freezing. Okay. The strong nuclear force is greater than the force of repulsion between like charges. I'm just going to draw some nonsense that'll hopefully help you make sense of this. You and I both know this should never happen. These two things should. How can I get these to stay together? Just two magnets you buy at the store. Two ceramic magnets, two for $1. How do I stick these two together permanently?
Glue.
Yeah, if you're in my house, you're using hot glue. Okay? If I just do this little tiny dab of hot glue, is that going to last?
No.
I better hot glue it up, right? I need enough strength from the hot glue to overcome the force of repulsion, right? Yeah? So, in that analogy, the hot glue is functioning as the strong nuclear force. And the force of repulsion is still the force of repulsion, right? Now, if I put some magnet here and a magnet here, and I put a dab of hot glue, is the hot glue going to have any effect? No, no. The hot glue only works if the two things are touching, right? Same thing with the nuclear force, the strong nuclear force. It only works when two things are, its effect can only be felt over the distance of a nucleus. You get as far away as an electron is, and the strong nuclear force has no effect whatsoever. It's a tremendous force at a tiny distance and has no impact at all at anything else. So you literally have to have two hydrogen ions or nuclei hitting each other like dead on for the strong nuclear force to take effect. Now once it does, it is so strong that it will essentially, I'm going to use the word glue, and it's not glue, but it is going to glue or Velcro two protons that want to fly apart. It's going to stick them together. Okay? something else happens in the process, which we'll talk about in a minute.
Nuclear fusion. Both nucleuses are fusing.
Yeah, you're on the right track, okay? So the strong nuclear force is greater than the force of repulsion between like charges. But there's everything going against this, right? Because these things do have the like charges. So if they get just near each other, but they're not perfect, they repel. And also, think about these two things, right? If I sling them at each other slowly, are they ever going to hit? No. They have to have these things have to be coming at the right velocity, at the right energy. The energy for this comes from heat. Okay? Fusion can only happen at the right temperature, and that temperature is anything above 12 million degrees centigrade, or 12 million degrees Kelvin. So we're going to say that to have fusion, like there's a black one here. Crazy hot for fusion to happen. At 11 million degrees, we're not having fusion happen. Even if you can get them to collide, they're not colliding with enough energy to stick for the strong nuclear force to take effect. And more than likely, they're not colliding at all. They're getting super close and then they're flinging apart. Why do they fling apart?
Go.
They repel. Why do they repel? They have the same charge. And please remember, these are tiny little things. Protons are tiny. To get them to hit head on, I mean, it either requires a precision you cannot imagine, or it requires so much just dumb luck. You know? But the sun's really big. It has lots and lots of hydrogen and lots of heat. So just through randomness, two of them hitting, that it happens all the time. All the time. And they stick. Okay? All right. What temperature is our sun? The core?
15.
15 minutes. So we're well above the temperature, right? If it cools off and we go below 12 million, what's going to happen?
It's gonna self-fuse.
No more fusion, right? It'll go cold. Okay. Now, I've skipped about a million things that the book would have had me teach you in a different sequence, but I don't think like the book, so. Let's talk about this. Erase this. I want you to talk to me about matter. You talk to me about particles. What are the particles? The fundamental particles. I'm talking about one. Protons. Name another one.
Electrons.
Electrons. Name another one.
Neutrons.
Are there particles smaller than these?
Quarks.
Quarks. What else? Gluons, mesons. We're not worried about any of those. Those are all good. There's one we do want to know about. It's neutrinos. So these are types of matter. Now we might be blowing minds in just a moment, okay? I know, I'm not saying that hyperbolically. Because in the universe there's not only matter, there's also antimatter. We're going to talk about charge and mass real quick on my matter. It's charge of a proton, positive. Charge on a neutron, neutral. Charge on an electron, negative. Okay. What's the mass of a proton?
1.
One what? You might be thinking of atomic mass unit,
Yeah,
which is good. But atomic mass unit is basically the mass of a proton. It's kind of like when we talk about, well, how big are these other stars? Well, they're 12 solar mass units. They're 8 solar mass units. They're 1 solar mass unit. How big is our sun? 1 solar mass unit, because we define a solar mass unit as the size of the sun. Like, you got to start somewhere. So a proton is 1. A neutron? It's really close to 1, but is it 1?
0.98 or something.
Yeah, I mean, it's just, oh, it's like right there. It's just a little less than 1. Okay, just a little, I mean, right there. How about an electron?
Almost like.
It's not 0, but it's almost 0. Okay? I mean, it's tiny. Okay? Lots of charge, big time charge. Almost no mass. No charge, big mass. Big charge, big mass. What's the charge on a proton?
Positive.
Positive. If I tell you I've got a subatomic particle, it's 1 atomic mass unit and it has charge, what are you telling me it is?
Proton.
It's a proton. Except for in this one. There's something called an antiproton. It's the size of a proton, but it has the opposite charge. Isn't that wild? There's also something called a positron. It's the size of an electron, but it has a positive charge. This matters. I'm just getting everybody a chance to kind of catch it. I'm not going for dramatic pause or anything. Just
What did you say about the anti-proton?
The antiproton, it has a negative charge, but the mass of a proton. It's as big as a proton, but the exact opposite charge.
So does neutron just transfer over, or?
Yeah, a neutron has no charge.
Yeah.
Yeah. So when we talk about matter and antimatter, we're focusing on what's the mass and what's the charge. We're used to thinking of this, right? This is all you've ever encountered. This is all you've ever been taught in science and earth science and biology and chemistry. This is all we ever talk about. Nobody ever talks about this until you get to like weird physics, right? Or this class. But we're talking about this for a reason. E equals mc squared. It says that I can convert energy into mass. It says that I can convert mass into energy. Okay. When I convert energy into mass, that implies if I have enough light, enough whatever energy source, I can conjure mass out of nowhere, right? Will it be a proton? Will it be a neutron? Will it be an electron? Will it be a positron? Will it be an antiproton? What's it going to be? Well, laws of physics have proven, demonstrated, hypothetically, theoretically, and also we've done it. Whenever we have, in particle accelerators and everything else, whenever we have made matter from energy, you get 2 types, always. You get both matter and antimatter in equal proportions. If you take enough light and you put it together, you slam it together at just the right velocity and angle and everything else, and I realize this sounds like science fiction or whatever. It's not. And you are able to produce a proton, you will also produce an antiproton. If you're able to produce an electron, you will also produce an anti-electron. Always in equal proportion. Does that make sense? It's going to matter a lot coming up. Not sure how to read the room right now.
Can't get one without the other.
No, you can't get one without the other. The opposite is also true. When I put matter and antimatter together, the matter will always be converted into energy instantaneously. So, a proton, what's its mass? 1, what's its charge? Positive. An antiproton, what's its mass?
1.
What's its charge? Negative. What's true of opposite charges?
They attract.
They attract. So if I am able to convert energy into matter, and I make one big and an antiproton big of opposite charges, what are they going to do right away? They're going to collide into each other. And what are they going to do now? They're going to generate energy. That's what we see. That's what all the experience of the colliders and particle accelerators and everything, it all does that. And this is what's happening in a star, by the way. This is part of what's happening in fusion. It's not happening with protons and antiprotons. It's happening with electrons and positrons. Positron is a type of, what are the two types of antimatter that you need to know?
Proton and positron.
Antiproton and positron. You've got to know those two. What's the charge on a positron? It's in the name. Positive, but what's its mass?
Almost 0.
Almost zero. It's the same mass as an electron, right? It's like the upside down world version of an electron, right? Somewhere in a galaxy far, far away is, you know, this other particle. Same thing for an antiproton. If an antiproton and a proton come into contact, what do? They combine, they cancel each other out, and energy is released. And you can count on it happening because opposites attract, right? I mean, statistically, it's near impossible to get two protons to run into each other so that the strong nuclear force takes over and we begin doing fusion. But it takes nothing. You don't need anything for a proton and antiproton to collide. It's not two north poles, it's a north and a south coming together. You can almost guarantee it, right? Same thing with a positron and electron. So if in nuclear fusion I produce a positron in the first step, which is what happens in the very first step of nuclear fusion, and I'm in plasma and there's just electrons flying around and they're negatively charged, what's going to happen? The positron is going to slam into an electron and they're both going to go poof. And we're going to release gamma rays. This is what happens in the first, part of what happens in the very first step of nuclear fusion. Okay. Put your pencil down for me. Is it true that whenever matter is produced, it's always produced in equal parts?
Yeah.
Why do you believe that?
Because you can't have one without the other.
And why do you believe that?
That's what the results seem to show.
Why do you believe that?
E equals MC squared.
Why do you believe that?
Jesus told us.
Thank you. It's that belief is no more reliable than I am. You believe it because I said it. And you paid money to be here. And you hope that Dr. Erickson didn't hire some idiot. Just a hair above idiot, right? But you're trusting me. And when I teach it to you, I didn't do the experiment. I'm trusting a lot of other people, right? But people who are a whole lot smarter than me have run all these experiments. And even before they ran the experiments, all of their thought experiments and all their philosophy, everything they did said, boy, there should be equal amounts of matter and antimatter in the universe. How does science say that everything came into being? How does an evolutionist teach you that everything in the world came into being?
Well, I understand
Yeah,
from what I
lots of
learned in
cool-
college, there's not an explanation yet.
They become
The Big
multiple
Bang.
ways.
Big Bang. So everything into this incredible singularity, and then bang. All this energy goes flying out, right? And energy converts into mass. And it should convert equally into matter and antimatter, right? There should be, for every proton you see in the universe, there should be an antiproton somewhere. For every electron, there should be a positron. Agreed? And wherever the two shall meet, they should cancel out and produce energy. Yes? Everything we know, everything we observe in the universe says that this is true. And yet it's not what we see. If this were what actually was, now we know that it's what should happen experimentally and theoretically and everything else, but if this is actually what, if there were really the same number of protons as antiprotons and electrons as positrons, you couldn't exist. Because every time a proton ran into an antiproton, they'd cancel out and become energy. Every time an electron ran into a positron, they cancel out and become energy, and they're attracted to each other. So of course they're going to run into each other. You'd have whole helium atoms and anti-helium atoms, and they'd get near each other, and the whole thing would go crazy. And yet here you are killing the game, because there's way more matter than there is antimatter. I mean, it's not even close. There's way more matter than there is antimatter. And this is one of the fundamental questions or issues of astrophysics, is where did all the antimatter go? Why is there not all this antimatter in the universe? Why do things exist at all? Because according to physics, the world doesn't look like it's supposed to. They have no answer. And yet, this is how physics works. So where did it all go? Why are you here existing as matter and not just energy? I would posit to you that only a divine creator can go, I'm going to let this matter exist. And if you don't believe in a creator, you have no answer for this whatsoever. It's a huge problem. Okay? I think that's real important for you to understand. And get there from, I didn't just take some leap because I want you to believe in the Bible. We're right here. I mean, if you read the book, it tells you this is probably the fundamental issue and question in astrophysics. No answer. It makes no sense to the ones who don't believe in a creator. Well, let's talk about neutrinos. So neutrinos are the word neutro sounds like neutron, right? The idea of neutral. They have no charge. They do have mass, but like almost none. I mean, it's almost massless. Which thing am I going to be able to throw harder at you, Nick, faster at you? A bowling ball or a golf ball? A golf ball, right? Bowling ball might hit harder, but the fact is I can get greater velocity on a golf ball because it's so much smaller, right? I could throw, theoretically, an electron a lot faster than I can a proton. Because this, relatively speaking, this has huge mass and this has almost none. But a neutrino makes an electron look like a mountain. I mean, these things really are almost massless, which is why they go just below the speed of light. These things are almost the speed of light. So you've got a particle with no charge, almost no mass, traveling at the speed of light. Does it interact with things? Not hardly. Not hardly. You can get a couple inches of lead and you can stop every gamma ray. That's light, which is massless. But a neutrino can pass through. Whew, it's just unbelievable. The speed they're going at, the size they are, the frequency of their wavelength, these things really almost don't interact at all, which is why we didn't know they existed. A neutrino has never bothered you in your life. They're passing through you right now by the trillions. You don't know. And you wouldn't have any way of knowing. I mean, again, it sounds like science fiction. But the science says there had to be a neutrino. Because remember, we can convert mass into energy and energy into mass, but when they did that for the fusion that we're going to be looking at later on, it didn't add up. There was mass missing. And so they hypothesized, hey, there's got to be some kind of a little particle that has almost no mass, but it's a little bit of mass, and it must not have any charge because we can't detect it. I'll call it a neutrino. And that's how it went for a long time, until eventually they were able to, I'll show you a video on this, about neutrinos. So they were able to come up with an instrument that could detect them. But even then it wasn't detecting them all. And they found out, well, there's actually 3 types of neutrinos. They call them flavors. I don't know. So these are you need to know a proton, an antiproton, a neutron, an electron, a positron, and a neutrino. Those are particles and antiparticles you must know. Okay. What time is it? All right. I really want to dive into fusion right now. That is the question. You're going, nope, you already warmed me up. What if I introduce you to an overview of fusion? I'll show you a video, and then I'll cut you loose and we'll go into the details Wednesday. Sound good? Okay, let's do that. I make no illusions this video is going to be boring. Okay? It's just,
Thursday, right?
huh?
You mean Thursday, right?
Thursday, yes. Yes. We got that for Monday. So I'm going to show you a video that it's not fascinating. It's going to wear you out just a little bit. Just watch it. Just get in the overview of it. We'll come back next class. We'll break it down. I will hand you like the diagram that the guy uses, and I will hand you 3 copies of a blank version of it. Because on your test, you'll have to fill this joker out. Okay? And all the things that we've talked about, they're going to be in this, and that'll be good for you. Here we go.
Related videos, please subscribe. Welcome to Stellar Physics 5D. In this video, we're going to cover the proton-proton chain, which is one of the 2 mechanisms in which hydrogen is fused into helium that takes place inside us. I rated the physics level of this video as intermediate. Now, way back in Stellar Physics 1D, I went over the various nuclear fusion stages in the stellar cores, and I covered in some detail the proton chain. But that was a while ago, so let's recap what I went over in that video.
You don't need to draw
Stars
this.
in
I'm
the
going to give you
main
this.
sequence stage, which is most of their life, are made up of roughly 75% hydrogen and 25% helium. They are supported against gravitational collapse by fusion taking place in their cores. And during the main sequence phase, that's hydrogen fusion. So hydrogen fusion takes 4 protons, which are hydrogen nuclei, and converts them into 1 helium nucleus, or alpha particle, which is made up of 2 protons and 2 neutrons. So the way this works is, you start off with 2 protons here, they come together and fuse into an H2 nucleus, otherwise called a deuteron. So in this,
So, and I'm sure he'll say this, there's a reason that one of those lobes is blue and one of those is red. One of those remains a proton, the other one's a neutron. Charge on a neutron is? Neutral. Charge on a proton is positive. They have nearly the same mass, but one of them suddenly has, when they collide together, suddenly one of them has no charge. Where'd the charge go? And what was the charge? It was positive. Where'd the positive charge go? You need some little tiny subatomic particle that has a positive charge, and you have one. It's a positron. It kicks off a positron right away in step one and becomes a neutron.
the process, a positron is emitted, which converts one of the protons into a neutron. This positron will immediately bump into an electron and annihilate into two photons. The force that is responsible for converting neutrons into protons and vice versa is the weak nuclear force. And anytime you have a weak interaction, you also have to have an emission of neutrinos. So this means that anytime you capture or emit a positron or an electron, a neutrino will also be emitted. Neutrinos pretty much don't interact with anything. Specifically, they only interact with the weak nuclear force. And as is suggested by the name, the weak force is weak, so those interactions don't happen very often. And so essentially, the neutrino streams out through the star without interacting with anything. So this is just energy lost. The energy carried away by the positron is not lost because it annihilates with an electron, converting into photons, which is then absorbed by the material in the star. Okay, so then the deuteron will bump into another proton, and they're going to fuse into a helium-3 nucleus. Then the helium-3 nucleus will bump into another helium-3 nucleus, which
That's why it's showing it with two like parallel chains, and then the two chains are coming together. You got two hydrogen ion or nuclei slamming into each other, forming a deuteron, and you got another two hydrogen nuclei slamming together, forming a deuteron. Then each of those, you have another hydrogen nuclei coming into it, forming a hydrogen-3 nucleus. And then you have two hydrogen-3 nucleus coming together, and that's the step he's at here.
pneumatic was made via the same process we just described, but it doesn't have to be. You just need a helium-3 nucleus from somewhere, and these two bump in together, and they fuse into a helium-4 nucleus, an alpha particle, and pop off two protons.
Laundry day could be a free electricity day.
Come on.
The net process is that 4 protons plus 2 electrons are converted into a helium nucleus plus 2 neutrinos, and I wrote plus 6 photons, but probably a better way to say it is just plus some energy, because photon number is not a conserved quantity, so writing it as 6 photons is probably not the best way to do it. The net energy released will be
You do not have to know the net energy released. What you're going to have to know, let me just stay here one second. Let me go get this for you. I'm going to hand it to you, okay? And then you'll have it. Okay. This is that. I mean, quite literally, like I took a screenshot of it, right? And then below, I took the same thing and you know, Microsoft painted it. That's enough for today. Have this. Look at it if you want. Come back next time and make this make sense.